Hello everyone. Welcome to Controllers Tech. This is the continuation of NRF24L01 video, and this is the third and final part. In the first two parts we saw how to configure the common section of the NRF, and in the second video we configured the transmit mode. This video will cover the receiving part. Let's continue from where we left off. Let's go back to the NRF.c file, and write a function to configure the RX mode. This function will take two parameters: the address of the receive data pipe, and the channel number. We have a very similar code that we had for the transmit mode. But we still need to modify few things. So let's go back to the datasheet, and check the registers. Now we have to enable the RX data pipe, and I am choosing the pipe 1 to receive the data. Later I will choose pipe 2 also, but for now, let's go with pipe 1. To enable this pipe 1, we will write a 1 to the first position of this register. Write 0x02 to the register. But this way we might disable other pipes, which are already enabled. So we will first read this register, and then only modify the bit 1. This way other bits remain unaffected. Next in line we have the RF channel register. So write the channel number to the RF channel register. This is already done, so let's move on. Now we have to set the address for the data pipe. We chose the data pipe 1, so we will set the address for the same. Data pipe 1 takes 5 bytes for the address. Let's write the 5-byte address for the data pipe 1. Now we have to set the data size for the data pipe. We will set it to maximum 32 bytes. Since we are not using dynamic payload, the receiver will always receive 32 bytes of data. Some of it might be the garbage values, but we will take care of them later. Write 32 to this register. Then there is nothing left after this, so let's go back to config register, to power up the device. We need to set the 0th bit, to enable the receive mode. And also the first bit, to power up the device. This is for the RX mode. Before we receive data, we need to check if the data is available in the FIFO. To do that, we will write a function, isDataAvailable. The parameter of this function will be the pipe number, so that we can check a particular pipe for the data availability. This can be done in the status register. The 0th bit of this register indicates if the TX FIFO is empty, or not. But we are interested in bits 1 to 3. Whenever there is data available in any data pipe, the respective bit will set here. As you can see, the values here can be between 0 to 5. So all we have to do here, is check the respective pipe number. If the bit is set, that means the data is available. Other than these, we also have to look for one more bit, and that is RxDR. This is a data-ready RX FIFO interrupt, and it sets when a new data arrives in the RX FIFO. So here we will read the status register. And then check for the bit number 6, that is our XDR bit. Note that the RX pipe number bits start from the bit 1, so we will check the pipe number by shifting it to the first position. If these conditions are satisfied, we will first clear the RxDR bit by writing a 1. And then return a 1 to indicate the success. Or else return 0 to indicate that the data hasn't been received. And the last function will be the NRF receive function. This function will be used to copy data from the data pipe into our buffer. The parameter is the pointer to the buffer where you want to save the data. We have to follow the same steps what we did in the transmit function. But this command here will change. Instead of payload send command, we will use the payload receive command. This will inform the NRF that we want to receive the data from the data pipe. Here we will send the command. And after sending the command, we will receive data using HOL SPI receive. Here we will receive 32 bytes of data. Once the data has been received, we will flush the RX FIFO. These are all the functions we need for the receive mode. Let's copy these functions in the header file. Now I am going to create a new project, where I can receive the data. Here I am using STM32 F446RE controller. Let's give some name, and click Finish. I will do a quick setup, like I did for the other microcontroller. Here also I am using SPI1, and I will keep the usual pins. Other than the regular SPI pins, we still need to select 2 pins for CS and CE. I am selecting PB6 for the CS, and PC7 for the chip enable. Let's enable the UART, so that we can see the data on the console. Click Save to generate the code. Here is the NRF connector I am using to simplify the connection. As you can see, it has 6 pins for the connection. And this is how it is connected to the controller. With clock, MOSI, MISO, chip select, and chip enable pins. I have also connected the interrupt pin, but as I mentioned, we are not using it today. Here I will just copy those libraries that we have created so far. Now change the CS pin and CE pin definitions. Let's include the NRF.H in our main file. Next we have to define the RX address for the data pipe. This address must be same as the address to which the transmitter is sending the data to. And create a buffer where we can store the data. Now let's initialize the NRF. and set the NRF in the RX mode, the address will data the RX address, and the channel number 10. Now in the while loop, we will check if the data is available. If it is, then we will receive the data into the RX data buffer. And finally transfer this data to the UART. This should be RX data, not RX address. Let's debug this now. Let's put a breakpoint inside this function. We got the hit. So the receiver is able to receive the data. Let's open the serial console to see the data we are getting. Run it again. You can see we are getting hello world, but along with that we are getting some garbage data too. This is because we are transmitting 32 bytes, but our data is actually less than that, and the same goes for the receiver also. Let's check it in the Hercules. Here also we have the extra Z. Anyway, let's add a breakpoint and check the data that we are actually getting. You can see, we are receiving hello world, and after that, there is terminating characters. This is our queue, we will check up to this terminating character only. To do this, I am using string length function, to get the length of the string. Let's change this to character pointer. You can see the controllers on the top right. Now we have the proper string. Also note that the LED in the transmitter is blinking, so the data is being transmitted. And we already know that the receiver is working well, because we are able to see the data. I am holding the reset button on the transmitter, and the data transmission have stopped now. It started again. So everything is working well so far. Let's see what happens if I look for the data in pipe 2. As expected, we didn't get any data. This is because the transmitter is only transmitting to the pipe 1 address. Now we will set up our receiver, so that it can receive with pipe 2. To do that, we have to enable the data pipe 2. This can be done here. We have to write a 1 in the second position. After enabling data pipe 2, we have to set the address for data pipe 2. This part is little confusing, so pay attention. As we have already discussed, that the 4 most significant bytes for the data pipe 2 to data pipe 5, will be same as data pipe 1. So we have to set up the address for the data pipe 1 also. Here the most significant address byte is 0 cross A. And 0 cross EE is the least significant address byte. So I am going to modify this least significant byte here, and set it to anything other than 0 cross EE. And we will write this address to the pipe 1. For the pipe 2 address, we can only write 1 byte of data, and here we will write 0 cross EE. So pipe 2 address will be made of 4 bytes from pipe 1 address, and 1 byte from pipe 2 address. Also, we will set the payload size for pipe 2. I don't need to give this pointer here, as that function will take care of it. So after I tested, it wasn't working, and I had to reconnect the power to the board. I found out that it has something to do with the reset values. So I wrote a function to reset the NRF. You can use this function to reset the status register, or the FIFO status register, or all the registers. There is nothing special going on here, we are just writing the reset values to the respective registers. These reset values are given in the datasheet in front of every bit of every register. Now when we initialize the NRF, we will reset the registers first. I am passing 0 here, because I want to reset the entire NRF. You can pass any value, other than 0 cross 07, and 0 cross 17. In the transmit function, after checking the FIFO status, we can reset it. Let's test the second data pipe now. We are receiving the data, and it's working well. If we check the status register, this time you can see the second bit is set, and that means the data has been received in the pipe 2. So everything worked out well. We were able to do a simple transmit-receive between two NRF24L01. By the way, I have NRF24L01 and 01+, and the data transfer works well between the two. If you face any problems, you should test the transmit code separately, like I did in the second video. Once you are sure that the transmit is working, then test the receiver. Also, you can create a function to read all the registers, and print them on the console, just to make sure that the values are set as per your requirement. I will include that in the final code anyway. This is it for this video. Later, I will buy some more modules, and I will make another video for multi-receiver, and also for shockburst mode, and for dynamic payloads. This will have a separate playlist, so it's easier to access these videos. You can download the code from the link in the description. Keep watching, and have a nice day ahead.